Okay, good. Well, thank you very much for giving me the opportunity. And as it has been said, I wear two hats. So I'm also within NOMAD or FAIRmat, the FAIRmat consortium, but I'm also the user, or at least the people in my group are users. And actually, I include myself in that. And I have this title slide here, which really I like to show because it shows that electron microscopy is one name, but it includes a lot of different techniques. So that you have diffractometry, spectrometry, you have microscopy images, you have multidimensional data sets, and you have time resolved experiments, in situ experiments, and so on. So it really includes a very wide range of techniques. And just to show you the environment that we're working in. You're taking here, I guess. I showed this already yesterday, but we're now in the CSMB building here, and the physics building is just across the little street next to it. And there are a number of microscopes that belong to different labs, right? So there are different institutions owning and running them, but we want to really have a common data strategy where basically we also then share all the experiences that we all have, of course, with our own NOMAD installations, but also be able to share then codes to analyze our data, and I will come to that at the end. Right? I've been asked what kind of hardware do you run for the data management, research data management, and our NOMAD Oasis runs actually within a little rack that we have within the department's computational infrastructure. And so we bought a few servers there over the years. So it actually, we had basically started with one and it became two and so on. Then we realized we also need to do heavy data processing. And so we invested also in GPUs. So we have a few high-end GPUs, and even last year we bought another one that is one of the top ones that you can currently buy. I guess they doubled their capacity in less than 2 years, so it's already outdated probably again. But what we made sure is, and this was also a question that I was asked yesterday, how do you actually then make your data storage future-proof, especially when you have such large data sets? And so we bought one of these JBOD extensions. So it's basically a server that has only very limited computational power, but it's called JBOD. JBOD stands for just a bunch of disks that you can then add to your server, which then basically is the storage where all the data can be placed. And we bought a server that has enough space for 60 disks. And if you can imagine, currently hard drives can have like 20 terabytes or even more. You can imagine that this can easily go up to above the petabyte. We have only filled it basically 1/3 or so we still have place to add more disks in the future, which is our strategy to deal with, somehow making ourselves at least prepared for a few years. Let's see what we have available in 10 years. We can't really plan for that. But really our system is basically prototypical for exactly this setup that you can find on the website for NOMAD Oasis. So the users actually interact with the NOMAD Oasis. The instruments actually upload their data directly to the NOMAD Oasis. So there is a service that runs once a night. And of course, if you want to have it earlier, you can also do this, start this upload manually. But the data is uploaded automatically from the microscope to the NOMAD Oasis. Not all the data, we're in the process of really automating also the indexing so that it becomes then available immediately, but that's not available for all instruments. It's only available for one instrument so far. And then we have, in our case, it's in the same rack, also some, I would call it high performance computing, at least in our limited view of what that means. Of course, this is not what you would normally call high performance computing, but for our computational needs, this is, well, I should say barely enough. Sometimes we wish we have more, but it basically is then separate servers that we can then send our processing requests to and then get the result and then have that stored in NOMAD Oasis again. Of course, we also use that then to publish data on the global NOMAD instance. Right, so my outline, first let me highlight what are the research data management needs in electron microscopy, because they may be different from some other labs, but also similar to some labs that don't have this E and M in the name, then I would like to really mention the Nexus format, which is what we use to actually store our data, and give you some pros and cons for that. Then also we have an activity of really also uploading old data that we've collected over the past 10 years to really include that as well. And there are some challenges associated with that. And then this Nexus Search app, which actually is linked to somehow this Nexus format, really helps us to then deal with all the data that we upload. And then we really make also use of the NOMAD Remote Tools Hub. For our needs, this is really perfect, and I'll show you more on that. So let me start by getting into research data management needs for electron microscopy. We have these instruments which then can, as I said already, upload their data directly to the NOMAD Oasis, but that's only the final step of the experiment. So there are a lot of manual steps involved, and I guess this is common for a number of techniques where you have some manual operations. For example, you need to prepare some chemicals and produce some kind of material. And in our case, even if we get the material already from our collaborators, which is pre-characterized with whatever technique they have available, we still need to make a TM specimen out of it that's thin enough for the electrons to go through. And this is something that we also need to document. This is a manual process, and that is something where one has to somehow keep some kind of electronic lab notebook. And now this is also available within NOMAD, and that's actually very good. But different people produce different results. So this is really something that is difficult to really standardize completely. And then also you have, of course, during the experiment, your sample rate change and documenting all that, documenting all the different sensors of your microscope. We still have a ways to go there. And there are activities actually where this is more and more complete, but not there yet, definitely. And then this is something that's, I guess, the first two are common probably to many techniques. This third point probably as well, but maybe not as many. We have many detectors that sometimes acquire data simultaneously. And the fourth point here, actually they do this sometimes at very high data rates. So we have a camera, for example, that collects data at 2 gigabytes. Oh, actually, it's more than 2 gigabytes per second. And if you can imagine that once for a few seconds, you collect many gigabytes in a single data set. So a data set can be 20 or more than 100 gigabytes at a time. So this is really something that you don't want to ship basically between computers all the time. So that's why we're very happy about the capability of our NOMAD Oasis to do online data processing, and this the NOMAD Remote Tools Hub that NOMAD provides is for us extremely useful. Right, but something that is then probably often not specific to our case is this last point here, that all these different instruments store the data in different formats. So you have from text to proprietary binary formats that nobody really knows how to interpret unless somebody does reverse engineering, but this is only basically 95%. There are still some unsolved mystery bytes in there and so on. This is really something that we have to battle with a lot because sometimes companies move to a new format, but you still don't have an interpretation for their previous format, and I will come to that as well. So this is basically what we're dealing with, and that's what part of the solution is, that we convert everything to the same format. Right, so I just had a few examples of basically company names that are active in the field, and they're probably also active in some other fields. But here I have this example down here where detector formats change over time. Right, so you have companies that provide an instrument, and then sometimes they partner with a different company that produces a detector, and then with maybe 3 different companies that produce other detectors. So you have a camera, you have maybe a second camera because you want to have direct detection, you want to have CCDs, you want to have EDX, you want to have all kinds of detectors, and they can come from different companies, and they all then update their software independent of one another. So you have also changing data formats. So I have this example down here from this company called Gatan, which makes cameras for electron microscopy, where you can see they have, at least they changed the ending of their file name so that you can actually sort of link to what they've done. But these are all proprietary formats. I guess the final one, the DM5 here, that actually is some description of it. And so there's some HDF5 internal standard, but they don't really commit to really sticking to this. So there can be, next week, there can be a new kind of data field being in there that you haven't known about. And then it also varies between installations. So, and then also even if the ending of the file stays the same, the content in the file is not standardized. So we've even had the case where basically from one installation, so you go to one microscope, maybe in the same lab, but they're different installations. So you see basically the same data item that you're looking for. For example, in microscopes, this is sometimes the spherical aberration can be stored under 5 different names. And this is really critical, of course, if you want to then make sense of the data, where do you find whatever you have? And this is a real problem. So, and companies, I think companies don't, they don't want to basically harm you with changing their format. It's just because, of course, they develop their instrumentation. It has new needs and new data needs to be stored. And so they find, okay, the old format doesn't deal with it. And so we have to somehow expand on it. So it's, and they don't want to take the time, and it's a lot of effort to actually standardize this because that would also lock them in, right? So it's not in their, they don't want to somehow intentionally, I think, at least that's my interpretation, somehow hide their information from us. But they don't want to take the effort to really standardize and make it open, because then they will have to document every change they do and make it public again, which is a lot of effort and costs personal months. Right. That's why we really rely on this external, we call it external harmonization or pre-harmonization of the data. We try to convert all the data into a common data format, which we then have also developed. We now have the head of FAIRmat, went through a 2-year process or longer. I guess you can ask Marcus for the details to actually get then the standard somehow accepted by the community for this Nexus format. And there's now pynxtools is an open source software that converts different data formats into this Nexus format, not only for electron microscopy, also for spectroscopy in optics and for XPS and so on, and Adlershof tomography and different techniques. Even scanning for microscopy is another way. So maybe you've heard about the story that this old story where people were building this tower, and then all of a sudden they started speaking different languages, and they had to stop the project because they couldn't collaborate anymore. And this is really where I think we need to define common metadata standards. So if we don't have common metadata standards, it really makes it difficult, and there's a lot of information lost in translation between different techniques. Here's a good example that you may have heard about. This Google subsidiary company, DeepMind, developed this AlphaFold software, which from protein data, they were able to now, using some complex artificial neural network, predict how proteins would actually fold once the sequence of the amino acids is known. And the data they used for that is from very different techniques. So it's from X-ray diffractometry, so from X-ray diffraction at synchrotrons typically, from nuclear magnetic resonance, but also more recently by electron microscopy. It actually is now in the process of overtaking X-ray diffractometry, because this is going down because so many structures are being solved by electron microscopy. Very different techniques, very different types of information that are collected, but it was all then reduced to the same basis. So the meta information and also the information about where the atoms and so on has been then reduced to the same format. And this is extremely powerful because all this data could then be used to develop this machine learning tool here. Without that, it would not have been easily possible, right? And so that's why I think this is really important to somehow have common metadata standards so that we can really compare apples with apples across different disciplines. And so this is why this Nexus standard has been developed, where electron microscopy is also part of it. And of course, there are many roads that lead to Rome, as we say in German. So there are, of course, a number of plugins being developed for specific techniques, which that have their place, definitely, because they have the advantage that you can, if you are a programmer and you can write this plugin, then you can quickly ingest your data into your NOMAD Oasis instance and can visualize it. You have basically a short time until you have results available. On the downside, if you first need to develop a data format that everybody agrees on, it takes a long time because you want to have the agreement of the community that somehow buys into this, or at least supports it to some degree. And this takes a long time. As I told you, if you really want to make it a standard that's accepted, it can take several years. And that's in the case for Nexus, for example. However, once you have this standard and once you have something that you can convert to, it can be done outside of NOMAD. So you don't need to change your NOMAD Oasis instance to incorporate a new format. You convert it to this common format, keep basically this metadata structure. You may potentially add something, but keep as much as you can, and you don't have to change anything in NOMAD. Whereas if you want to incorporate a new data format by a new plugin, you have to really change something in your NOMAD Oasis instance, which means that this change is only going to apply to your local instance at first, unless you somehow make it some kind of open source software, which people then, which is then incorporated into the NOMAD distribution, which then other people, when they update their NOMAD instance, would also benefit from. But because if everybody includes their own data into NOMAD, it's very difficult to keep the data model coherent. Because if there are many people trying to import data into it, then of course it's difficult to really keep some kind of standard. Whereas if you really first agree on a standard, you also have the time to really make it coherent with the data model that's within NOMAD. So I would say the left one is really for local installations where you have a one-of-a-kind experiment that you don't really need to share with a lot of other groups. Whereas if you have some, for example, commercial instrument or so where you want to ingest data from that is being sold across the globe to other labs as well, then actually it really makes sense to first convert to a common data format and then go that route. And both are possible within NOMAD. So we have a lot of, in our NOMAD instance, or I should hurry up, we have a lot of different instruments that have collected data for many years. And these are available on these instrument computers. And so we really wanted to also incorporate these into NOMAD, our instance. And that really has been more difficult than anticipated because these formats, as I've told you, already changed over time. So Markus Gruber, who's sitting in the audience here, he's really invested a lot into even understanding all these different formats because there's no documentation about it. So this is, and then of course also how people store their data, the meta information. I mean, if they keep a paper logbook, that typically is not accessible anymore if it's from 10 years ago. And if they somehow store some sample information in the file name, everybody does it differently. So what we ended up doing actually is we ended up someone dumping the whole data tree into an Excel file and having an extra column where we then add as much information as we can manually extract from the file names and maybe some background information we have in our mind about the users and so on. So this is really some effort that we're going through, but then ultimately we can harvest basically this old, this treasure of existing data already. And hopefully then for the future we can at least, if we don't change anything, at least somehow standardize the way that people store their data. Right. Yeah, let me, but once you have the data and even this old data, right, down here you can see the timeline. This is only from one instrument that was more recently installed, but since 2020 it was active, and we can basically see there are many uploads now that even before we had NOMAD, we can now really have inside NOMAD, which is really nice because we can make use of, for example, for machine learning and so on, of this old data. And that really helps then also to document new data sets. So you can then, once you upload this data in this Nexus format, you can interact with it in NOMAD very nicely. You can look at all the metadata. You can zoom into the data and so on. Of course, if you want to do more, you need to do online processing. But one thing I also wanted to show, Marcus has also downloaded a number of data sets that are publicly available within, for example, the Nodo and Mendeley data and so on, and some other websites. So there are some 4,000 data sets in electron microscopy only for a specific technique in there, which are now available that we can compare with. And this really helps in also documenting our own data, because and this is, for example, one of the data sets. They always are linked, or typically linked with some DOI, some paper or so. When people upload the data, they typically do this when they publish a paper. And so we now have this workflow that extracts the paper, summarizes the paper, produces a short summary, and has basically a description that can then go with the data. And this really then helps to also auto-annotate our own data, right? So if the data looks similar to what we have, with all the metadata that we provide, this tool will then, in the future, not yet, help to really suggest also annotations for our own data and make it easier for people to document their own data. Right, I won't be able to go into the Remote Tools Hub. Just to say as much that you can run Jupyter notebooks, you can run, for example, also graphic user interface, all within basically this NOMAD installation, and that's super useful. Having basically now a 10 gigabyte data set that's been uploaded here, and there's some LLM that then processes the data. So we actually share a lot of data with external users, so they come to us to experiments with us, and we then send them a link, here's your data, and they typically don't know how to operate our software, but we tell them, oh, there's an LLM tool. Just open that one and then ask it questions, and that as long as you know what you want to do, it actually walks you through the process of getting to your results. Anyway, I will stop here. This is my summary slide. Yeah, so we really have, in electron microscopy, we have a demand for a lot of large data sets, so we really need to have some local storage. At least that's what we decided. We didn't outsource this because there's also a cost associated with that. Once you have a little bit of money to invest, at least was our decision, we invested this into this computational and storage hardware. And in our field, at least, when you have instruments that are commercially available that also are existing in other labs, it really makes sense to first convert to a common data format, because, and there's one advantage, you can then ultimately, when enough people do this, convince, and in some cases we've done this already, convince the manufacturers to store in this format as well. And then you don't really have to worry about this conversion anymore at all, because the data will then be natively, without any effort, ingestible into NOMAD. So thank you very much for your attention.